Jai Hind. So today we are going to discuss about the applications of the operational amplifier. In the previous two lectures, we have discussed about the basics or fundamentals of the operational amplifier. That is, what is operational amplifier, why we call it as operational amplifier, what are all applications we can use, the basic concept of the virtual ground, and the block diagram of the operational amplifier. Also, we have discussed about the pin diagram, block diagram, and some applications like inverting amplifier and non-inverting amplifier. So we are in continuation with that, and we are starting with the first. So these are the contents: the practical op-amp, the inverting amplifier, non-inverting amplifier, buffer amplifier, summer amplifier, difference amplifier, integrator, differentiator. So here, this we have already discussed. This is the inverting amplifier. Here, whenever you apply any signal to the pin number 2, that is the inverting terminal, and the non-inverting terminal is ground, that is pin number 3 is at ground, and we take the output at the pin number 6, and here the feedback path is being provided, then such type of circuit is termed as the inverting amplifier. So whatever signal we apply in the inverting amplifier, we get at the output, we get the inversion of the signal, means 180 degree phase shift will be there, so that you will be getting your output equal to this. That means the amplified version, and how much amplification will take place, that will be depending upon the gain of this amplifier circuit, and the gain is nothing but RF by R1. Minus sign represents the 180 degree phase shift, and the ratio of the feedback resistance to the input resistance, that is R1, it will be representing the gain of the amplifier. So this we have already discussed in the previous lecture. Now, the next was the non-inverting amplifier. So in case of non-inverting amplifier, this is exactly the same circuit as that of your inverting amplifier, but the only difference is here the non-inverting terminal is grounded, that is pin number 2, through R2 resistance it is being grounded, and input signal is provided to the non-inverting terminal. So because the signal is applied to the non-inverting terminal, and that's the reason we are having the output that will be in phase that of the input signal. If this is your input signal, we input, this is the function of some time, then the output will be equal to this will be your V output, and this is in phase with that of the input signal. So we get the faithful amplification of the input signal, and the output will be equal to that will be in the same phase as that of the input signal, and the gain of this amplifier is giving by 1 upon RF by R1. So if you compare this non-inverting amplifier with the inverting amplifier, what are our observations? One is the 180 degree phase shift will take place in inverting amplifier. As the name says, invert, it's inverting. So that means it will invert the signal, input signal at the output side. Second is the gain. The gain is, in case of a non-inverting amplifier, gain is only RF by R1. Whereas in case of the non-inverting amplifier, gain is slightly increased by an amount of 1 plus RF by R1. So gain is slightly gets increased. So you will get more gain in case of non-inverting amplifier, and it will be in the same phase at that of your input signal. So here you can see this is the gain of the non-inverting amplifier. The next is the voltage follower. Voltage follower is also called as the unity gain amplifier or unity gain or it is also called as the buffer. Means unity gain amplifier means that whatever input you are applying, then the same same signal you will going to get at the output. So if the feedback resistance RF is equal to 0 and the resistance input resistance is equal to infinite, that means open circuit, then the circuit would be having a fixed gain of 1, and output voltage will be present on the inverting terminal of the amplifier. So all the output voltage will be present at the inverting terminal of the amplifier. So the voltage follower is also called as the unity gain. Why unity gain? Because gain of the this amplifier is 1. Why? Because output voltage is exactly same as that of your the input voltage. So what is the purpose? Why do we design such type of amplifier? What is the need of the unity gain amplifier? So if you remember, in case of the emitter follower, that is a common collector amplifier was having the characteristics that it was having input impedance infinite, and it has high input impedance and low output impedance, and the gain of that emitter follower or the common collector amplifier is unity, because it is a current amplifier. So the purpose of the emitter follower was it is used for the in the multi-stage amplifier to as an impedance matching device to reduce the loading effect. So the same purpose is the same type of the circuit can be generated or created with the help of the op-amp also. The transistor amplifier will do the same work, and the voltage your operational amplifier is again the same type of the amplifier which is used. So here the only thing is that we use only the single op-amp can serve the purpose in case of the unity gain amplifier. So this is the circuit diagram of unity gain amplifier. So you, if we observe or if we inspect carefully, so we can see that the gain is, we always use the negative feedback in operational amplifiers to reduce the gain. So that is the reason we always use the negative feedback. So here this is the negative feedback, and here the input signal is being applied to the non-inverting terminal. So this is the output is connected to the pin number 2, and your signal will be applying at the pin number 3. So if you draw the equivalent circuit of this amplifier, so here this is your pin number 3 and pin number 2, and we are having the virtual short here. So drawing the equivalent circuit. So let's say this is my pin number 2, this is my pin number 3, and between pin number 3 and 2 we are having the virtual short, and pin number 2 is being fed back to the pin number 6, and between pin number 3 and pin number and the ground terminal we are applying the signal, that is V input signal, and at the pin number 6 and between the ground we are using the voltage output. So if you look at carefully this circuit, because this is the short, so here V input will be equal to V output. So that means the gain will be equal to, so V out will be equal to V in, and we know the gain is equal to V naught upon V input, and that will be equal to 1. So this is how we get the unity gain in case of the unity gain amplifier or the voltage follower circuit. The third category of the next type of the circuit which is we are going to discuss is the summing amplifier. Summing amplifier is another type of the operational amplifier where we would like to add multiple input signals, then we use the summing amplifier. Summing amplifier, as the name says, that it sum up all the input signals which are appearing at the input terminal, and that summation will get multiplied with the with the gain of the operational amplifier or the in this summing amplifier, that will give you the desired output. So here if you'll see, we are showing the 3 input signals are being applied. So what will be the, how do we get this output? So suppose because of this V1, I1 current is flowing through the R input resistance, and V2 is due to V2 signal, the I2 current will be flowing, and due to V3, I3 current is flowing in the input terminal. So here we can increase these number of input signals as per your requirement. Now we'll write the nodal analysis. We do the nodal analysis, and let's say this is your point X and this is your point Y, and because of there has to be the virtual short or the virtual ground. Why? Because of the high input impedance of the operational amplifier. So here if we'll write the write the nodal doing the nodal analysis and writing the current equation, then it will be equal to I1 plus I2 plus I3, and that will be equal to IF plus IN. So IN is the current which is flowing here. But we know that the input resistance which is connected here, that will be, that input resistance is infinite, and because of that this I input will be equal to 0, and because I input is 0, so voltage across this will be equal to 0. That means this, and this is at the 0 potential, that means this point is also, X point will also be at the 0 potential, that means virtual short. So here in this equation, this I input will be equal to 0. Why? Because of the input impedance infinite. So your equation will be reduced to I1 plus I2 plus I3 is equal to IF. Now we reduce this current as that we can rewrite this equation in terms of the voltage and the resistance. So I1 will be equal to V1 minus, suppose at this point the voltage is Vx, so V1 minus Vx divided by R input plus V2 minus Vx divided by R input plus V3 minus Vx divided by R input. That is equal to IF. IF means Vx minus, this is the V0. So Vx minus V0 divided by RF. So here your Vx will be equal to 0. Why? Because of virtual ground. So if this is equal to 0, then your equation will be reduced to V1 plus V2 plus V3 divided by R input, that is equal to minus of V0 divided by RF. So V0 will be equal to how much? Minus of RF by R1 times V1 plus V2 plus V3. So we can easily see that because it is an inverting amplifier. Why it is an inverting amplifier? Because all the input signals are being applied to the inverting terminal. So, and in case of inverting amplifier, we have already seen that the gain of the inverting amplifier is given by the RF by R1. So, this will be the RF by R input is the gain of this amplifier, because here we have taken all the resistances they are same resistance, means they all are equal. So that's why the gain is RF by R1. In case if you are not having the same resistance, then it will be R1, this will be R2, this will be R3. So in that case, we will be getting the output voltage will be equal to minus of RF by R1 times V1 plus RF by R2 times V2 plus RF by R3 times of V3. So here the individual gain will be RF by R1, RF by R2 and RF by R3. If all three are taken as equal, then it will be, we can take out this RF by R outside the bracket, then it will be minus of RF by R times summation of all the voltages. So this is how we can find out the sum of all the voltages applying at the summing amplifier, input terminal of the summing amplifier. So this is the same thing. Now coming to the difference amplifier. Here is the difference amplifier. The most simplified difference amplifier would be something like this. If we are applying signal to both the terminals, that is, suppose this is V1 and this is V2. So if we are applying signal to both the terminals, then we call it as the difference amplifier. So whenever we are applying more than one input signal, and so here we can use the superposition theorem. So what is superposition theorem? Superposition theorem says that if you are having more than one sources in the circuit, then we can ground one voltage source and find out the output because of the one voltage source, and then in the next step we'll be grounding the next voltage source, and by using the second voltage source we will find out the output voltage, and then we sum up both the outputs and we'll get the net result. So here in this case, if first of all I am grounding the voltage V2 at the ground potential, then V1 is applied at the signal. Now this circuit has been converted into the inverting amplifier. So we know that in inverting amplifier, the output, let's say V01 equal to, and that will be minus of RF divided by R1 times of V1. This is, sorry, V1. Okay. Now, in the second case, we will be grounding this and we are using V2. So for that, this signal has been reduced to the non-inverting amplifier, and we'll be getting the output V02 is equal to 1 plus RF by R1 times of V2. Now, if you'll compare this RF by R2, it will be a very high value in comparison to 1. So because we can say that RF by R1 is much greater than 1. So we can neglect this value of 1. So V02 will be equal to RF by R1 times of V2. So net voltage V0 will be equal to how much? It will be V01 plus V02. So keeping those values in this equation, we'll be getting RF by R1 times V2 minus V1. So here you can see that with this circuit, when we are applying signal to both the terminals, the input terminal as well as the inverting terminal as well as the non-inverting terminal, then the output will be equal to the difference of these two voltages multiplied by the gain of the amplifier. So gain is given by RF by R1. So whether we are going to get at the output the inverting signal or the non-inverting signal, that depends upon that whether your V2 is greater than V1 or V1 is greater than V2. If V2 is greater, then definitely we are going to get the positive signal. If V1 is greater than V2, then we are going to get negative signal or the inverting signal at the output. So this is our output. Now this signal has been further modified. Here also we are having a voltage divider network at the non-inverting terminal. So if you compare this circuit and this circuit, so we can see that this is an additional circuit. So this circuit can be simplified very easily by using the voltage divider theorem. So to make this circuit is equivalent to this circuit, what we will do, we will be trying to find out the voltage across VB. So voltage across VB is nothing but the voltage which is appearing across the R4. So we can write VB is equal to R4 divided by R2 plus R4 times V2. So this we are doing by the voltage divider theorem. So here you can see this is the circuitry drawn here. So I1 will be equal to V1. Here they have done it differently. This is the another way of solving the problem. Here the KCL has been used. So I1 will be equal to V1 minus of VA. This is your VA times divided by R1. I2 will be equal to V2 minus VB divided by R2, and IF will be equal to VA minus V out divided by R3. So because this is the VA and this is VB, so these two are equal. Because why? Because of the virtual short. This is nothing but the virtual short, and VB is equal to, I have just told you that here VB is equal to R4 divided by R2 plus R4 times of V2. So here putting value of V2 is equal to this, and if V2 is equal to 0, then V out will be equal to minus of V1 R3 by R1. If V1 is 0, then again what we are doing? We are using the superposition, and when V1 is 0, then V out will be equal to this voltage divided by this is the voltage, and that will be equal to R3 plus R1. This is what? This is the gain of the non-inverting amplifier. This is, if you look at carefully, this is nothing but 1 plus R3 by R1. This is your R3 and this is your R1. So they have directly written it, but we know that, and the input voltage here, this is your VB. So basically this is nothing but, because of this terminal, when this is at the ground and this is at the zero potential, then we will be getting the output voltage V output B or V02 will be equal to V2 times of, that is this voltage multiplied by the gain, that is 1 plus R3 by R4. This is nothing but the same thing. Okay. So here V output will be equal to addition of these two voltages. So V output A, that is this value, and V output B, that is this value. We putting these two values in this equation and solving it, and we get the, and here we have assumed that R1 is equal to R2 and R3 is equal to R4. Then we get this output, that is R3 by R1, or sometimes we are instead of R3 we can use it as RF. So it is RF, or if this is the feed, this is nothing but the feedback resistance RF. So RF by R1 times V2 minus of V1. This is how we can get the output of the difference amplifier. Any kind of circuit can be easily solved by using this equation. So the next is the unity gain amplifier. Next is the integrator circuit. So integrator circuit, if you compare this with the inverting amplifier, the feedback resistance has been replaced by a capacitor C. So integrator op-amp produces the output voltage that is proportional to the amplitude and the duration of the input signal. So if you're applying any square wave, then at the output you are going to get the integral of the square wave, and that will be equal to the triangular wave. So in the next slide we'll be solving this the numerically, or we are doing the derivation that what will be the output of the integrator amplifier. So here again we will apply the KCL. So I input will be equal to, here in this case I input will be equal to V input minus of 0 divided by R input, and that will be equal to V input by R input. IF is equal to, that is the C d V naught by dt, and this is the basically how do we get the C dV naught by dt, that is dq C dq by dt, that will be the 1 upon C dq by dt. And so here this will be nothing but the current is what? The rate of change of the charge. So this simply explain that how do we get this equation. Basically here in this equation, if you write I input is equal to IF, and let's say this current is I1. So I input will be equal to I1 plus IF, and I1 will be equal to 0. Why? Input impedance is infinite. Op-amp input impedance is infinite. So here the I input will be equal to IF, and how do we write the I input? That will be V in minus Vx divided by R in, and that is equal to Vx minus, it will be basically you can write it as a Vx minus of V naught divided by Xc. So if you solve this, so it will be your equation will be equal to V out will be equal to, means it will be C. We know that this is C dVc over dt. So Vc will be equal to, this is basically equal to this. So here you can write it as here we can write it as C d, and Vc is Vx minus of V naught divided by dt. This is 0. So here you can write minus of C dV naught by dt, and that is equal to V input divided by R input. Solving this equation, we will be getting V naught is equal to minus of 1 upon RC integration of 0 to t. For one cycle we are writing 0 to t, and it will be equal to V input dt. So this is how we get the output voltage equal to, that is minus 1 by RC, that is the constant value, multiplied by integration of the input signal. So this is how we get the output voltage of an integrator circuit. Differentiator circuit is exactly same as that of the integrator circuit. The only thing is these two elements has been swapped. So here input in place of input resistance, in case of inverting amplifier we have placed the capacitor, and feedback resistance will be there, and we get the differentiator type of circuit. So here if you'll apply the triangular wave, you'll get the rectangular wave at the output. So again write the equation. So suppose this is your I1, so I input is equal to I1 plus IF, and here this is nothing but Vc is equal to C dVc over dt. This is the current which is flowing through this. So here you can write in place of here you can write C dVc over dt, and this will be equal to 0 because of the input impedance is infinite. So this is equal to, and IF will be equal to Vx minus V naught by RF. Instead of Vc, again we can write d by dt. Vc is nothing but equal to V input minus Vx. This is equal to Vx minus V naught by RF. So Vx will be equal to 0. Why? Virtual ground. Vx is equal to 0. Kyun? Because of virtual ground. So this is 0, this is 0. So he'll be having your C d Vn by dt is equal to minus of V naught by RF. Solving this, V naught will be equal to minus of RF times C d V input by dt. So here you can see that output will be equal to RF as RC, that is the some constant value, and multiplied by the differentiation of the input signal. So this is how we get the output voltage. So this is how we have discussed in this lecture about the unity gain amplifier, summer, difference amplifier or the subtractor, integrator and differentiator. So I close this topic, this lecture here. Thank you. Jai.